All right, so section 11.2, space coordinates and vectors in space. So when we're working in space, or R3, it's three-dimensional space. We have our axes, X, Y, and Z. And we are going to use the right-hand system where we have X coming out towards us. So the X-axis, the positive X-axis, is going to be coming out of the board or the table or the paper or whatever it is you're working on. It's going to be coming straight at us. So we obviously can't draw that. So what we'll do is we'll draw it with a bit of perspective on it, so at a bit of an angle. So there's the positive X-axis. Then we'll have the positive Y-axis going off to the right, where we used to have the X-axis, the positive X-axis in 2 dimensions, and then the positive Z-axis is going straight up. Okay, so if you just kind of think about laying the XY plane down on the table, turning it so X, the positive X, points straight at us, and then adding a vertical axis for the Z. That's what we've got. So this is that. Now, having 3 axes is going to create 3 coordinate planes. So I'm going to go ahead and draw the full set of axes here. So we've got our Z-axis, Y-axis, and X-axis drawn at an angle. All right, and something to be aware of when you're doing this for perspective purposes, you do not want to make the X-axis, the hash marks on the X-axis, the same distance as those on the Y and the Z. So from our current perspective, we are looking at the Y-axis from the side and the Z-axis from the side, but we're kind of viewing the X-axis from an angle. So those hash marks on the X-axis are going to look a little bit closer together. So for perspective purposes, I would recommend drawing those just a little bit closer together. And then on the Z and the Y-axes, drawing them at full scale, whatever your full scale is. Okay. That will help make it easier to identify in what octant these things are showing up in. So that was the next thing I was going to tell you, is that these coordinate planes formed by the XZ axes, the XY axes, and the YZ axes, those coordinate planes are dividing space up into 8 segments called octants. So let's draw on those planes. Draw them in simply by drawing lines parallel to the axes forming the plane. So this is our YZ coordinate plane. Okay, then we have our XZ, so I'll draw that through here like this. Oh, that was awful. One more time. Try to keep it parallel as possible. Okay, that was, again, absolutely awful. There we go. Not an artist. Definitely not an artist. So that's our XZ plane. And then finally we have, I'll do it in pink here, the YX plane. Let's see if I can draw that in. Okay. So I'm not sure how well that translates, but hopefully you can kind of see what's going on. The green is running up and down, okay, because that's that's YZ. So the green is running up and down. The XZ plane is slicing from us through the back of the screen. And the pink, the XY, I didn't write it down. The pink, the XY plane is laying horizontally here. So hopefully you can kind of see what's happening here. This is dividing our space up into 8 different octants, 4 octants above the XY plane and 4 octants below the XY plane. So it's going to be very, very difficult to see that here. Let me draw another picture for you. I'm just going to draw a box. Okay, so there's a box. I'm going to put the origin of this box at its dead center. So the Z-axis goes straight up to the middle of the box. The Y-axis goes straight out to the side of the box. And the X-axis, which is the hardest one to draw, is going to come right out the front of the box here. So we have X, Y, and Z. And if I were to continue these down, hopefully you could see we've got kind of 4 separate little boxes happening on the top here. Oops, get over there. There you go. Okay, so that's one. We have another one that comes forward. Okay, so that's 2. So this one in the front here, that's octant 1. This cube in the front, I'll try to outline it again. Okay, that's octant 1. Octant 2 is the one behind it. So this cube in the back here is octant 2. Let's grab another color. So octant 3 would be over here off to the side. Okay. So this would be octant 3 here, and then octant 4 would be coming forward around here. So they still just run counterclockwise around the z-axis, just like they did whenever we were doing quadrants in the plane. Okay, so that's 4. And then 5, 6, 7, and 8 are directly below these. So 5 would be down here. I'll just go back to white. 5 would be here. Not 4, I already did 4. There's 5, 6, back here, 7, underneath in the back here, and then 8 up at the front here. Okay. All right, so hopefully that helps you kind of see what's going on. But we've got 1, 2, 3, 4 around the top, and then 5, 6, 7, 8 down around the bottom. Okay, so a point in space is a coordinate triple. So we have coordinate pairs or ordered pairs in the plane. So now we're going to have coordinate triples or ordered triples in space. So we have ordered triples. So that's going to be X, Y, and Z. These are points in space. Triples. Okay. A vector in R3 are going to be just the exact same thing. We're just extending by one more dimension. So that's going to be V1, V2, and V3. That's our vector in R3. So this is our X coordinate, Y coordinate, Z coordinate, or X component, Y component, Z component. Okay, so we have that. Now, how do we find the distance between 2 points in space? Well, it's exactly the same as finding the distance in 2 dimensions, only now we have a 3rd dimension added on. So the distance between 2 points, let's not do yellow. There we go. So that distance is given by d equal to the square root of, and then we're just going to subtract the components. So we've got x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Okay. All right, and I didn't write it down, but that's given 2 points, x1, y1, z1, and x2, y2, z2. So that's how we find the distance between any 2 points. Okay. That's also going to give us the magnitude of a vector beginning at point P and ending at point Q. Okay, so another thing that we're going to be doing in 3-dimensional space is dealing with spheres and other conical shapes. So the equation of a sphere centered at point x naught, y naught, y naught, z naught, okay, is going to be given by this equation. X minus x naught squared plus y minus y naught squared plus z minus z naught squared equal to the radius squared. Okay, so there's our equation of a sphere. So we have our distance, equation of a sphere. The next thing we have is going to be the midpoint formula. So that's also very useful. So the midpoint formula in R3 is going to be given like this. So this is the midpoint between points x1, y1, and z1, and x2, y2, z2. Okay, that's given by this, x1 plus x2 over 2, y1 plus y2 over 2, and z1 plus z2 over 2. So again, all of these are just extensions of the exact same formulas in two-dimensional space. We're just now adding that third component to them. All right? Okay, so we are going to extend our standard unit vectors into 3 space as well. So our standard unit vectors in R3. So remember, the unit vector in the x direction was given by I, right? And it was 1, 0. Well, it's not moving in the z direction either, so the 0 component is also, the z component is also 0. J, same thing. We have 0, 1, 0 in the z direction. And then the unit vector in the z direction is given by k, which is 0, 0, 1. All right, so this is going to be our unit vector in the x direction, unit vector in the y direction, unit vector in the z direction. Okay. Okay, so a little bit more on vectors in general. Okay, if we have u and v are vectors in the plane, so u will be u1, u2, u3, v will be v1, v2, v3. We have several properties they're going to hold here. We're also going to need a scalar. And scalar c, which is just an element of the real numbers, which you can't even read. I went off the screen. Let's see if I can fix that. There we go. C is an element of the real numbers. All right. Then we've got the following going on. Number 1, u is equal to v if, and only if, u1 is v1, v2, u2 is v2, u3 is v3, etc. If and only if u1 is v1, u2 is v2, and u3 is v3. Okay, so that's equality. All right, number 2. If v is represented by the directed line segment from point P to point Q, so we've got P being P1, P2, P3, and Q being Q1, Q2, Q3, okay, and V is equal to PQ, then V, which is of course components V1, V2, V3, are just equal to the difference of the QP components, Q1 minus P1, Q2 minus P2, Q3 minus P3. Okay, there you have that. All right, the magnitude of V. So again, this is really just our distance formula here. So the magnitude of V is equal to the square root of V1 squared plus V2 squared plus V3 squared, or Q1 minus P1 squared plus Q2 minus P2 squared plus Q3 minus P3 squared. All right, there's our magnitude. The unit vector is going to be exactly the same thing. The unit vector in the direction of V is V divided by its magnitude, okay, or 1 over the magnitude of V times the vector V1, V2, V3, if you want it in its component form. Okay, addition of vectors, U plus V, you just add the components, so this is U1 plus V1. Second component, u2 plus v2. Third component, u3 plus v3. Okay, and finally, scalar multiplication, c times our vector is just going to be cv1, cv2, cv3. Okay, so there are our properties for scalars. For vectors in R3. Very much the same as what we saw in R2. It's just being expanded into that third dimension. And finally, we have parallel vectors. So, why did I just write that? I don't need to write what I said. Parallel vectors. Vectors u and v are parallel if there exists a scalar c, which is an element of the real numbers, such that u is equal to c times v. So in other words, if one of them is a scalar multiple of the other, something to keep in mind, vectors do not have to be going in the same direction to be parallel. C could be negative, it's any real number. As long as there is a real number that we can multiply to one vector to get the other vector, even if it changes the direction, those vectors are parallel. Okay, so let's do a quick example here. So suppose I've got, let's write the instructions first. Determine if u is parallel to v. So we're going to determine if these vectors are parallel. These are my little parallel bars, badly drawn, albeit. This is just saying, determine if they're parallel. All right, so u is going to be 3, negative 4, negative 1. V is going to be 12, negative 16, and 4. Okay, so we need to see if there's any way for us to conclude that this is the case. So for 3 to become 12, or for 12 to become 3, either way, what's the relationship? We're looking at that relationship between the x components, the y components, and the z components. All right, so we're looking for that relationship. 3 becomes 12 if we multiply 4 to u. Okay, so 4 times 3 is equal to 12. So is it possible that 4u is equal to v, question mark? And the answer is no. So let's take a look there. 4u is equal to 4 times the vector 3, negative 4, negative 1, which is 12, negative 16, negative 4. So it worked for 2 of the components, but it did not work for the third component. This is not equal to vector v. The problem comes from, let me get my red out, the z coordinate. The z coordinate of v is positive 4, whereas the z coordinate of 4u is negative 4. So no, these are not parallel components. I said components, I meant vectors. These are not parallel vectors. Okay, and we can use this concept to determine if 3 points are collinear or not. Are they on the same line in space? So let's write that down. We can use parallel vectors to determine. You know what? I don't like the way that came out. It's not that we're using parallel vectors. We're using the concept of parallel vectors. So we can use the idea of parallel vectors to determine if 3 points in space are collinear. Okay, so we can do that. We can kind of use that idea. If one of the vectors from one point to another point is parallel to a vector from the next point to the third point, then we've got it. So let me kind of draw what I'm talking about here. So suppose I've got 3 points in space. There's P, Q, R. Now in space, it is very possible that these are in fact collinear. Maybe they are all on the same line, just like this. But maybe there's some perspective going on here. So maybe I've got some perspective where this P point is actually closer to me than it appears, so that I get this but then I have to change direction to get back to R here. So maybe there's some perspective on this that I can't see because of the angle where I'm looking at these things, right? So the question we have is this collinear? Well, the idea is if the vector from P to Q is parallel to the vector QR, then they have to be on the same line. That's the idea. The same would be true for P to R, right? So P to R. If any two of these vectors are parallel, we know that these three things are collinear. Okay, so we can check those. So let's get some P, Q, and R points going on here. So point P, let's assign that 1, -2, and 3. Let's assign Q to point 2, 1, 0. And let's assign R to point 4, 7, -6. Okay, so let's find in component form what is PQ and what is QR. So PQ, that is going to be 2 minus 1, first component, 1 minus -2, second component, 0 minus 3, third component. Okay, so that is 1, 3, -3. Great. So now let's find QR. Okay, so that's 4 minus 2 for the first component, 7 minus 1 for the second component, -6 minus 0 for the third component. So that is 2, 6, -6. Okay, so hopefully you can see pretty obviously that these are in fact collinear because PQ is parallel to QR. And we can see that because if there exists a C such that multiplying PQ times that C gives me QR, we know we're parallel by the definition. So to get from 1 to 2, I would multiply by 2. So let's see what 2PQ is. Well, it's 2 times 1, 3, -3. So that is 2, 6, -6. And if you look, that's exactly what QR is. Therefore, there is a C, in this case 2, such that C times PQ is equal to QR. This does satisfy our definition. So we have that PQ is parallel to QR. Whoa, not bad. There we go. So this implies that PQ and R are collinear. All right, so that's the end of this section. If you have any questions, please let me know in the Q&A session. Of course, you can always contact the Math Lab Monday through Thursday from 8 a.m. to 8 p.m. using the instructions posted on the website. And you can email me anytime, and I'll get back to you as soon as I can.